In this video, we're going to do a simple application of Bayes' theorem to the case where we measured some quantity n times, and we're trying to figure out what the best estimate of the true value of that quantity. So for example, to make it concrete, you can imagine that we have a piece of rope and we've gotten n measurements of it. And then that the errors of the measurements are all independent from each other. So we have different people coming with different rulers or different techniques, and each person is measuring the rope. And every time they make an error, and the errors are all independent. So that's the kind of the setup we have in mind. So the true value of these n measurements is mu, but we don't know what the true value is, and we're going to try to infer what it is from having made n measurements. So the model is the following. We're going to say that d sub I, the ith measurement, is equal to mu plus some random error, epsilon sub I. And this epsilon sub I, we're going to assume that it was drawn from a normal distribution with mean 0 mean, so it's not, the errors are not biased on either side of mu. They can be bigger or smaller. And that the variance is sigma squared. And what this means, this notation means precisely this, that the probability of epsilon sub I conditioned on sigma squared is a Gaussian. So this is the Gaussian. This prefactor out here is to make sure that the probability distribution is normalized, that it integrates to 1. The variance is sigma squared, and the most probable value of this thing has its maximum when epsilon sub I is 0. So it's peaked at epsilon I equals 0. And also we're going to assume that all these errors are independent. So we'll assume alright, so this information is going to allow us to construct the likelihood function. And we'll also need to assign a prior probability to mu and sigma squared. So first let's deal with the prior. And this time, for simplicity, we're going to assume what is called a flat prior. In other words, the probability of any mu and any sigma is all equally probable. So we're claiming that we're completely ignorant about the most probable value of mu and sigma. So that is probably claiming to know less than we actually know, because if we're able to make the measurements, presumably we know lots of stuff about what we're measuring. And you might think we've already violated one of the desiderata of our robot to making inferences, in that we're supposed to use all the information we have when we're making inferences. But for this illustrative example, we're still going to assume that we don't know anything. In any event, we're going to end up showing that as long as we have a moderate number of measurements, what we've assumed for the prior is going to be almost completely irrelevant. And so the data is going to swamp the prior probability in our posterior distribution. So we don't have to worry too much about throwing away some information in this case. So the fact that we don't know anything is equivalent to saying that the probability of mu and sigma is proportional to some constant. And we also need to come up with a model for the likelihood, the probability of the data conditioned on the model, which in this case is the value of sigma squared and mu. So for the likelihood, what we want is the probability of the data, and I'm going to write it this way, d with an underscore, condition on mu sigma squared and the background information. And d is going to be a column vector of these n measurements. And our model, remember, is that each d is equal to mu plus some error, so this can be rewritten as mu times a column vector of 1s. This is an n by 1 plus a column vector of these errors. And so this probability, since all the errors are assumed to be independent, we can just multiply these probabilities. So this is going to be equal to the probability of epsilon 1 times the probability So this particular data set we have, its probability is going to depend on the probability distribution of epsilon 1 multiplied by the probability distribution of epsilon 2, and so on all the way up to epsilon n. And the reason we can just multiply these probability is because we've made them independent, right? If they were not independent, then what we would have to do is the probability of the whole set. We couldn't factor it in separable pieces like this. And so now we can plug in our expression for each probability, and this gives us 1 over, and we're going to have n factors of square root of 2 pi, so that's 2 pi to the n over 2, and we're going to have n factors of sigma, so sigma to the n, and then we're going to have n of these factors, but each time with a separate I. So remember that the product of two exponentials is the exponential of the sum of their arguments. So that's going to simplify to exponential minus 1 over 2 sigma squared times the sum from I equals 1 up to n of epsilon sub I squared. Now we're going to rewrite this epsilon sub I squared in the following way, this sum here. So remember that the sum is equal to, right, because if I take the dot product of epsilon vector with itself, I get epsilon 1 squared plus epsilon 2 squared and so on. So I can just write it as epsilon vector epsilon. And I'm going to use this notation all the time from now on. And so the probability of the data conditioned on mu and sigma squared Right, so here I have epsilon transpose epsilon, and from this expression I know that epsilon is equal to d minus mu times 1. So over here I can write this 1 with an underscore is this vector of 1s, and d is this vector, like I defined it over here. So if I subtract mu times the 1 from d, I get back the epsilons. And so I'm going to substitute this in this likelihood function. And now I could use Bayes' theorem to invert this probability to get the probability of mu and sigma conditioned on d. So Bayes' theorem says that the probability of mu and sigma conditioned on d and I is proportional to the probability. This is the prior, and this is the likelihood. So the prior, the likelihood function. Now in this case, since I picked the prior to be a constant, and I've said that the posterior is proportional to this quantity, we can completely ignore this. The fact that it doesn't depend on mu and sigma means that it drops out of the problem. And so this is what we're going to use. This likelihood function is going to help us determine what mu and sigma. And this quantity up here is the posterior probability. Okay, so the posterior is which is equal to this prefactor of 2 pi to the n over 2 doesn't depend on mu and sigma, so we can just forget about it since we're only have the problem up to some arbitrary proportionality constant, which we can determine in the end by insisting that the posterior probability is normalized. So we can ignore this factor, so it's going to be 1 over sigma to the n. Right, and now we're going to rewrite this expression in the argument of the exponential function in a more convenient way. So remember, this is just the sum of the differences between the data and this model mu times a column vector of 1s. All right, so what have I done here? So it's good to do a little bit of geometry at this point to explain what I've done. So This is the sum of the squares of the data minus the model. Mu times 1 is the model. That's how we think the true value of the data are. They're based on some true value mu times a column vector of 1s, the difference of that, and this is the sum of the squares. So this is a sum of squares, and we broke it up into the sum of squares of two quantities, mu1 minus this mu hat times 1, and the squares of d minus mu hat of 1. Now what is that? What's that picture? So let me make a picture. So this is the data vector d, and this over here is the model vector, which is a column of 1s, and we're going to assume that this vector here is mu times 1, so up to here, and this vector here, well, first let me which is the projection of d onto 1. I'm going to call that mu hat times 1. So this mu hat is the length that when you project this on here. So this is 90 degrees here. And this vector over here, I'm going to use red for this one, is going to be E. E for error. All right, and so this quantity over here, this vector, that's d minus mu times 1, right? If I go to d and I subtract mu times 1, I get this vector. So this is d minus mu times 1. And so the breakdown I did here is just a Pythagorean theorem, right? So it says that this vector mu1 minus mu hat times 1 gives me the length of this one. That's this one, the sum of the squared length of this one. This length over here is mu1 minus mu hat 1. That's this vector. And so this is the sum of the squares of this bit. And this one, E, is this d minus mu hat 1. So this one is d minus mu hat 1. This squared plus this squared is equal to this quantity squared. All right, I hope that's clear. So that means that I have the following. Mu hat, right, is the projection of d onto this column vector 1. So mu hat is equal to 1 transpose d divided by 1 transpose 1. Right, this is the normal equation that you'll remember from the lecture on projections. And what does this mean? Well, the 1 transpose 1 is just this. It's just n, right? It's 1 plus 1 plus 1 n times, because the vector 1 has n components. And 1 transpose d is equal to 1, 1, 1 multiplied by d1, d2, all the way up to dn. So that's just going to be d1 plus d2 plus d3 is just going to sum the d's. So this formula is just 1 over n times the sum 1 to n of the d sub I. So it's just the arithmetic mean. Okay, so I can use this to rewrite this expression here. Posterior probability. So it's the exponential of minus 1 over 2 sigma squared times the sum of two perfect squares. And this one can be simplified further. So I can factor out the column vector of 1's. And so this transpose this quantity so it's equal to mu minus mu hat squared times n. Remember, 1 transpose 1 is just n, like we've worked out over here. And this quantity is E, so this is just E transposed E, this bit here. Transpose E. So the sum of the squares of what we call the residuals, where this is D minus the model evaluated at mu hat, where mu hat is just the arithmetic mean of the data. So the reason we're going through all this linear algebra is that this is going to generalize later on to, we're going to do a straight line fit and then more complicated model with more and more parameters. All right, let's use this probability density function for mu and sigma to draw some conclusions about mu and sigma. And the first thing we're going to do is try to find the most probable values of mu and sigma. And for that, we would find the maximum, the location of the maximum of the posterior probability. That can be done using calculus. We just take the derivatives of the posterior with respect to mu and set it equal to 0, and then take the derivative with respect to sigma and set it equal to 0. And we'll get two equations and two unknowns that we can solve for. Now it's convenient when doing these maximization problems to first take the logarithm of the posterior probability function. And the reason that is going to give the same answer, it's because the logarithm is a monotonically increasing function, so where the logarithm achieves its maximum is going to be the same place as where the argument of the logarithm achieves its maximum. And so let's take the log and then take the derivatives. So to this end, I'll define this function L of mu and sigma, which is just defined as the log of the posterior probability. And that's going to be equal to, so I take the log of the first term, that's going to be minus n log of sigma, and then plus the logarithm of the second term, and since this is an exponential, I just need the argument. And now I can take some derivatives. So first I'll take the derivative with respect to mu. The first term is independent of mu, so this vanishes. And then the second term is just going to be this part that depends on mu. Remember, E transpose E depends on mu hat, but not on mu. Mu hat's just a constant. And so I just need to worry about this term. So I get, and that's that. And the 2's cancel. And I set it equal to 0 at the maximum. So that means that the maximum is at mu hat. This quantity is going to be 0 when mu is equal to mu hat. And in fact, we can just tell from here, just by looking at it, that mu equal to mu hat has to be the maximum. This is an exponential function with a negative, so it's going to have its maximum where this quantity here is the smallest. This is a sum of squares, this is a sum of squares, so everything is positive. And so the smallest we can make it is going to be when mu is equal to mu hat, then this term will vanish. And so the maximum is at mu hat. Implies that mu hat equals to this quantity here, just the average, is the most probable value of mu. Then I could take the partial derivative of L with respect to sigma and set it to 0. And if I want to find the max, I set the derivative of this to 0 at the maximum. So the maximum for mu is at mu hat, so I'm going to evaluate this at mu equals mu hat and sigma equal to sigma hat, and then if mu is mu hat, this term vanishes and I'm just left with the E transpose E. So now I want to solve for sigma hat, so I'll multiply through by sigma hat cubed, and this will give me minus n sigma hat squared. One will cancel from the bottom, minus E transpose E, which means that the most probable value of sigma is equal to E transpose E divided by n squared. I might have two minuses. I did a sign error somewhere. Oh, this is a plus here, right? Plus. And this is a plus. This is like this. Yeah. So therefore, sigma hat is equal to E transpose E square root divided by n. And remember what E transpose E is. E transpose E is just the sum of the squares of the residuals. So it makes sense that that would be a good estimate for the variance, because it is the sample variance when I subtract off the mean. All right, so we found the most probable value of sigma hat and the most probable value of mu. But we can do more than that because we have the whole probability distribution function. So in fact, we can get a better estimate for the uncertainty of mu by first marginalizing out the value of sigma. If I integrate this function over sigma, then I will be left with the probability distribution for mu alone, independent of what sigma squared is. So marginalization . And now I have a univariate probability distribution function for mu alone, and I've integrated out the parameter sigma. So now the posterior of mu alone, independent of what sigma is a better estimate for the uncertainty of mu. And we're going to do this integral next.